Okay, so today we're going to talk about continuity and some theorems, just to review those. We really care a lot about whether functions are continuous. We talked about that with limits a little bit, but this is kind of my little summary of what you need to know about continuity. Remember that a continuous function is one you could graph without ever lifting your pencils up. It has no holes, no jumps, no breaks, no asymptotes. If a function reaches its intended height at a particular x value, then it's continuous there. That means if it has a y value for the x value that you're plugging in, then it is continuous. If a function is undefined but still possesses a limit at a given x value, then there's a point of discontinuity. We say that's a removable discontinuity. That would be like a hole in the graph like this. If you had a hole in the graph, but it keeps going. Remember, we defined that a removable discontinuity is a discontinuity that you could fill in with one little hole, like one dot would fill it in and make it continuous. It's not a jump, it's not a break, it's not an asymptote. That is non-removable discontinuity, which is the last thing here. Infinite discontinuity is caused by a vertical asymptote. Jump discontinuity is caused by a break in the function, and both of those are examples of non-removable asymptotes. Jump discontinuity would be like this. Like if you have this, and then it jumps up here, right? It jumps up. If it's a vertical asymptote, then that's a infinite discontinuity. You don't really need to know all those, but you probably should know the difference between removable and non-removable. So we have this AP workbook that I don't really make you buy anymore, but I do have copies for you of this page. So page 86, 87, numbers 1 through 6, there's a handout for you. I want you to spend maybe like 10 minutes working on this at most if we need it. And I just want you to pause the video, and then when we're ready to go over this, no more than 10 minutes, unpause the video so we can talk about it. And just so you know, you're going to do the additional practice one starting, it's on page 86, additional practice numbers 1 through 6. So unpause this when you are ready to move on. Okay, so I'm assuming you've had a few minutes to work on this. So let's talk about these. The first three just say use the definition of continuity to decide whether each of these functions is continuous. If it's not continuous, explain why it's not continuous. Well, number one's one that shows up every now and again. Remember what that means? That's the greatest integer function. So right away, if you remember what the greatest integer function looks like, that's a step function. And at each whole number, it steps up. So if you remember what that means, that means every number between 0 and 1 rounds back to 0, and then every number between 1 and 2 rounds back to 1. Every number between 2 and 3 rounds back to 3. And then it would go up and continue like this, which means at x equals 3, you should see that there's a problem here because there's a jump in that graph. So is it continuous? No, it has a jump discontinuity. Number 2 is our favorite. You're definitely going to see these on the AP exam. We want to know, is that continuous at 0? We should be pretty good at this. We talked about this with limits yesterday. You got to check to see, is it the same? Is it the same value when we plug 0 in there? And you should be able to see pretty easily. If we plug 0 in the top, we get 0 plus 5, which is 5. If we plug 0 in the bottom, well, there's nothing to plug in. You just get 4. 4 does not equal 5. So if you were writing your answer, like explaining it, we would say no, that there's no jump discontinuity. In terms of limits, we could say no, because the limit as x approaches 0 from the left of g of x does not equal the limit as x approaches 0 from the right of g of x. In terms of continuity, again, that's going to be a jump. It jumps from 4 to 5 at 0, or a non-removable discontinuity. Same thing for number 3. Again, plug 2 in and see what happens, and you should get 4 for both of those. If you plug if you plug 2 into the top function, you get 4. If you plug 2 in the bottom function, you get 4. So because those meet up, they have the same limit, we can say that number 3 is continuous. Number 4, first part A, shouldn't be so bad because they just give you some values for A and B and ask you, is that continuous? Again, you're just looking to see where they meet up. So they tell you if A equals 3 and B equals 2, is that continuous? Well, if A equals 3, you get 3x squared, and B equals 2, you get 2x. Check to see at 3 if that works. Well, if I plug 3 in the top, I'm just going to get 0 plus 1, which is 1. If I plug 3 in the bottom, I'm going to get 3 times 9 plus 2 times 3. Well, that's definitely not 1, right? That's like 27 plus 6, which is what, 33? I don't know. I'm just going to put not equal to 1. So for part A, is it continuous? No, because they do not meet up at x equals 3. There's a jump at x equals 3. The limit as x approaches 3 from the left doesn't equal the limit as x approaches 3 from the right. Something like that. Part B, something I've seen on AP tests. Describe all values where this is continuous. So what do we know that continuous functions have to do? They have to meet up at that point at piecewise functions. So at x equals 3, do you agree that both of these pieces need to be equal to each other? So I could say the absolute value of x minus 3 plus 1 needs to equal ax squared plus bx. And remember, I want to know that at x equals 3. So I can plug 3 in there. And 3 minus 3 is really just going to give me 0 plus 1 equals 3 squared times a would be 9a plus 3b. And you can't actually tell me what A and B are because I don't know. They could be multiple things. But you just want to give the ratio there. So you could leave this as your answer. You could solve for A or B. I think the answer book for this one actually solves for B, and they say, well, that would be 1 minus 9a equals 3b, or b equals 1 minus 9a over 3. Right? As long as you have some version of that, of being able to simplify it, knowing that you can set them equal to each other. To be continuous, they have to meet up at that point, and so that's how you can set that up. Number 5, which of the following functions are continuous for all real numbers of x? This is knowing these functions. Number 1, the absolute value of x. Is that a continuous function? Yes, it has a sharp point, but that still means it's continuous, right? So number 1 is true. What about tangent of x? Is tangent a continuous function? Well, if you think about tangent, tangent is undefined at certain places. Tangent is sine over cosine. If you think about the graph of tangent, you probably don't remember what it looks like, but it looks something like this. And it just keeps having asymptotes. So number 2 is not continuous. It has asymptotes. What about number 3? What's the graph of number 3 going to look like? It's a parabola, which means it's a continuous function. So 1 and 3 are true. 2 is not true. So E should be your right answer. Again, those are very common AP questions. And from that first AP test practice, you should have seen those. Those are kind of tricky sometimes. Number 6 is extra tricky. because they give you this really big function here. And it says, which of the following statements is true? And they're talking about all these discontinuities at 3 and at -3. A really common answer here would be to say, well, I can factor the bottom, and that would factor into x minus 3 and x plus 3. And since those are in the denominator, that must mean they're asymptotes. So I'm going to pick D because that means there's asymptotes at 3 and -3. The problem is they could be a removable discontinuity, which means the difference between a whole and an asymptote is that if a factor is in the numerator and the denominator and you can cancel it out, then that means there's just a hole in the graph, or a removable discontinuity. So the problem with number 6 is, how do I factor that? And the answer is, it's kind of tough. You can't factor it. What you can do is you could do some synthetic division. I'm trying to see, is x minus 3 a factor of the numerator, or is x plus 3? So I could try to synthetically divide it. And do you remember what happens when you synthetically divide? If it is a factor, what do you get left over? 0 as your remainder. So I just tried, if x minus 3 was a factor, that means I could divide out 3. And I'm going to take those coefficients. You could do long division if you want, but I think synthetic division is a better choice.